project them all in the sphere, they cover up some area on the sphere. So let's say that is maybe our scan area. And remember our definition of solid angle is if a sphere has a radius of r, our solid angle is defined as a scan over r squared, a non-dimensional quantity, area divided by radius squared, and solid angle has dimensions of steradians. And actually, I don't know if I actually gave this definition before. I'm talking like I gave this definition before, but I don't think I did. And this is a two-dimensional analog to our definition of a angle that you're should be more familiar with. If I have a circle and I have an arc length on that circle that's subtended by this angle theta, theta in radians is s over r in radians. So that's the analog. And of course, in a complete circle, there are 2 pi radians in a complete circle, and in a complete sphere, there are 4 pi steradians, right? Because the area of a sphere is 4 pi r squared. So if my area covers the entire sphere, it is 4 pi. I'm sorry, 4 pi r squared area, dimensions of area. Okay, so this is kind of a generic way, depending on how I scan. I mean, I could have a very narrow beam. Let's say I scan just up and down like that, or I could scan over some area like I illustrated on the first one here, and it's kind of a way of coming up with a single number without having to define those details. Okay, in any case, I'm going to go do the same conservation of energy argument that I gave when I derived the radar equation from before. However, I'm focusing my beam. I have some power going into my antenna, and all of that power has to be captured over the sphere. So the difference is when I looked at my definition of the radar equation at making a measurement, I'm looking at a single beam and I'm looking at the instantaneous power density within that beam. Now if I say I'm going to scan over some area for some averaging time, let me see what the definition was that what the term that he used, scan time. Okay, so now I'm not going to talk about the instantaneous power, but I'm going to talk about the hour, the average power over some period of time t sub s. So my measurement is not going to be instantaneous. It's going to be average over the time t sub s. Okay, so over the time t sub s, my beam, however narrow that beam is, whatever my gain of my transmitter is, I'm going to be averaging that power over that area a sub scan. So my power density now of my transmitter is PT over the area that I'm scanning, or my area that I'm scanning I can write as my solid angle, capital Omega, R of the transmit distance squared. And I'm going to keep a separate transmit receiver just so we can kind of get a better idea how the equation is derived, and then I'm going to reduce it to the monostatic case. Okay, so in this case I'm now talking about an averaged power over a scan time t sub s. And now if I go through my radar equation, my receiving antenna, I assume is also scanning at exactly the same time, but since it's always pointed at the direction of the beam, I'm not averaging the received power over at t sub s, over my area that I'm scanning t sub s. I'm constantly rotating my receiving antenna, so it's always pointed at that beam. So on my receiving end, I got my transmit power over my averaged area during my scan. I have my scattering cross-section as before, but then on the receiving end, my effective area of my antenna is exactly the same, because it's not, I'm not looking at average over that large area, because my receiving antenna is always rotating to be aligned with the transmit antenna. And then I have my loss 4 pi r receiver squared, my spreading of the signal from reflection off of the target out to the received antenna. So all of this together gives my received power. That should be P sub r, received power. And in the way the expression is written on the next page, I kept the receiving antenna in terms of an effective area, but remember, we can convert that effective area to a gain, just by using lambda squared over 4 pi gain for the effective area. I'm not sure why in the version of the equation that's given in the notes they didn't do that, but this gives our received power. So basically the same as, very similar to before, except my transmit power now is averaged over this large area. And then of course I can always include a loss term. We have the same loss as before. Now for my noise, again it's the thermal noise, so I have a white noise from a thermal source, and the bandwidth. Now this is where things get, where you have to think about the time I'm taking my measurement. So if I'm making my measurement over a time period t sub s, that sets my bandwidth of 1 over t sub s. So if I think about that, I'm going to average a signal for a period of t sub s. Fourier transform, bandwidth is 1 over t sub s. I don't think I worked through all the math on that before when I was introducing Fourier transforms, but I think it's kind of a basic idea. What you might want to think about is if I have a sine wave that has a frequency of b hertz. So this will be the highest frequency sinusoidal signal that my filter will pass, or maybe I may also say that the lowest, the cutoff frequency, the lowest frequency that the filter would attenuate. So my period will be 2 pi radians per, oh wait, no, I'm not doing it in radians, I'm doing it in cycles. So my period will be 1 over b seconds. Right? So if I have a b cycles per second, 1 cycle, period of 1 over b seconds. So if I now have my averaging time equal to t sub s, if t sub s is equal to 1 over b, you see I've completely averaged that sine wave out. So the average of that signal is 0. But if I have anything lower, so if I have some b less than 1 over t sub s, I'll see that it won't average out. There'll be some non-zero output from that signal. So that kind of gives a simple explanation without going into the Fourier transforms as to why we have this relationship between bandwidth and what maybe could be called integration time. All right? So I now put these together, signal to noise ratio. I have effective area of the antenna, sigma p of the transmitter, transmit power, divided by 4 pi receiver distance, transmit distance squared, solid angle of my scanning, my loss, and then my noise, kt sub s times my averaging time, little t sub s. And for the monostatic case, where my gains and my distances are the same, A sub E, scattering cross-section, transmit power, T sub S, 4 pi, again, R to the fourth, sigma L K T S. So the only thing that really changed was I just set my two distances equal. Okay, which should be what I have down here. Average power, effective area, T sub S, scattering cross-section. What happened? Effective area, scattering cross-section, PT, T sub S. 4 pi, solid angle, R to the fourth. 4 pi, solid angle, R to the fourth. Loss, K, TS. Loss times the thermal noise. Loss, K, TS. Okay, so those are derived. All right. So some typical numbers for the pulse repetition rate, duty cycle 10%. That looks like a really high number for power, but 100 kilowatts. Pulse repetition frequency, 1,000 pulses a second. Some examples of radar cross-section. Maybe I should go say a little bit about radar cross-section. Remember I said this is like an idealized area, and so an object like this, I guess, is supposed to be some type of reentry vehicle. Depending on my geometry, in this direction, it has a scattering cross-section of 0.001 square meters, because it's looking kind of almost straight onto it. But in this direction, I have a much larger scattering cross-section. So this is a typical type of measurement that could be made on aircraft, on spacecraft, on any type of vehicle, even on natural phenomena like snow, hail, raindrops, because they make, if you're wanting to measure those with radars, where we look at the scattering cross-section as a function of the geometry. And so again, this is a very common thing that's modeled, common thing that's measured. Obviously, if you're in the defense world, you'll want your radar cross-section to be small in certain directions. So that's a feature of geometry, as well as the type of material that the object is made of. And I think I had kind of a sketch here. This again is from the notes on the MIT lectures. Obviously things that are like flat plates, like the rudders on the missile guidance system. I would expect that in this direction, those would have a really large radar cross-section, but in this direction, they would have a very small radar cross-section. If they're built of material that can absorb energy, that will have the equivalent of a perfect reflector, take a much smaller size. So radar cross-section is a big consideration in design of systems for many different reasons. This is some example numbers of different types of aircraft, boats, other vehicles, stuff like that. So okay, I think I'm going to stop here. And again, I hope you saw the first lecture from the MIT presentation before this. And then in next class, I'm going to talk about how we actually make the range and Doppler measurements, and how some of these design parameters affect the precision of those measurements. Okay, so you should all be able to see this. If there's any problems with the videos, let me know, and I'll see everyone on Wednesday. Thanks a lot.